Day 18 is heat and temperature and German sausages, German food, because you have to cook them and it takes thermal energy. Anyways, what is heat? Heat is the flow of thermal energy from one object to another. Thermal energy and heat are two different things. The heat is more of the flow of that energy. Um, there are different types of energy that we've talked about, or maybe I've mentioned before. You may know of kinetic energy is one. There's electrical, kinetic, electrical, potential, and those are just to name a few. But there are lots of different forms of energy. Thermal energy is just another form. Temperature and thermal energy are not the same thing. For example, thermal energy, as you know, we've kind of talked about this, is Q is equal to mc delta T. Now, temperature makes up the thermal energy. But what we haven't talked about is there's different ways of generating thermal energy. I could easily say that Q is equal to F sub kd, where F sub k is your frictional force and d is your displacement. That is also thermal energy. So, in essence, your thermal energy and temperature just cannot be the same thing. The temperature can be an indication of your thermal energy, but it's not the same thing because there are different ways of generating thermal energy. As I pointed out here, friction generates thermal energy. You know that if you rub your hands together, or if your older brother drags you across the carpet, and you get rug burns. Those are all examples of thermal energy. The change in the change in temperature of an object indicates a change in thermal energy, as noted here. The temperature change will directly indicate your thermal energy. And as I said before, there are many forms of energy: thermal, electrical, mechanical, chemical, etc. We've seen a few before, or at least I've talked about. The little apparatus that you didn't get to see in the lab that was described in the lab for you basically takes electrical energy, runs it through a coil, and then converts it to thermal energy. Since we can measure our electrical energy, which from the last lab is 12 volts times 10 amps, and then multiply that by the change in time, that'll actually give us how much energy we put in the system. Thermal interaction between objects. Whenever two objects are having different temperatures come into contact with one another, there is an energy exchange. The energy will flow from hotter object to the cooler object. This is a not quite a quantum mechanical phenomena, more of a thermophysics phenomena that occurs, but it always goes from hot to cold, where your hot object is going to lose energy and your cold object is going to gain energy. This interaction will continue until some thermal equilibrium is reached. At that point, they reach the same temperature and there's no net flow of energy at equilibrium. For example, moving on down, we have two objects. We have a cold object and the hot object. The cold object is going to be creamer. I don't drink coffee, but today I do. The hot object is coffee. So you have cold creamer, hot coffee. Basically put, if I have my hot coffee and I put my cold creamer in there, what's going to happen is my hot coffee is going to slightly decrease in temperature. Let's make sure these are proportional. It's a tiny little arrow. And then my creamer is going to significantly change its temperature. So it's going to go up very high. You can't think of it as a mixture. Yeah, I know it is a mixture. It's creamy coffee. But you have to think of it as two separate entities, your coffee and your creamer. So as you notice, their temperature changes are not going to be the same. Your creamer is going to heat up way more than your coffee is going to cool down. But what is the same are their energies. The energy gained from your creamer plus the energy lost by your coffee. So here's cream, and here's coffee, is going to equal 0. Because if, let's say we have it in a really good thermos, then we are not going to lose energy to the environment. And so what that means is energy gained by your energy gained by your creamer is equal to energy lost by your coffee. And so this is this is a conservation of energy. It's one of the many, 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 many ways that energy is conserved in physics. So conservation of energy is because energy is not actually being lost to the environment, it's just changing forms. The negative sign by convention indicates the heat energy is lost. And we do know that E is equal to mc delta T from earlier, or if I wanted to expand it, I could say Tf minus Ti. And so if we set them equal to each other, we get what I call the conservation of energy, which essentially is mc delta T is equal to mc delta T, but with subscripts. If I want to distribute the negative, I get this down here, but I tend to think that this is kind of confusing to students. It seems to always be. And so I'm just going to scratch that out. It's just sometimes it works for some students. They'd rather not have a negative out front because they'll tend to forget it. But I don't know, I think this one's a little bit more logical. And notice that they're different TFs. Most of the time, I can't think of many instances where it doesn't happen. Your temperature, your final temperature is going to be the same. So TF1 should equal to TF2, which we could just simply call TF. This will work for a complex system as long as all objects gaining heat on one side and all objects losing heat on the other. Now, this equation works well if you want to solve for like the mass or specific heat. But what if you need to solve for final temperature? Well, that's when it gets a little complicated. So I kind of gave myself some room on the next slide here. Let's say I take it and distribute it. M1 C1 TF minus M1 C1 TI1 equals M2 C2 TF. Sorry, negative M2 C2 TF plus M2 C2 TI2. That ends up becoming a positive when the negative gets distributed. So if I move my TS all to one side, that gives me M1 C1 TF plus M2 C2 TF equals M1 C1, it's not a 1, there, that's better, TI1 plus M2 C2 TI2. So now you got positives on both sides. Basically, once again, what if I need to solve for the final temperature? So if I pull out my final, my TF here, that's going to give me M1 C1 plus M2 C2 equals, and I'll put dot 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 to say it's the same thing, and then divide both sides, I get a completely new equation. M1 C1 TI1 plus M2 C2 TI2. Oh wow, that's a, oh, I got an idea. Oh, this is brilliant. Ah, this is good. You're gonna love this. You're gonna love this. I can make straight lines. I learned how. What? Oh, this is great. All right, and that's over M1 C1 plus M2 C2. Look at that straight line. Okay, so this is handy when you need to solve for the final temperature. It's not handy when you need to solve for a specific heat. This is nothing magical. All it is the conservation of energy. When you set the energy gained by your creamer equal to the energy lost by your coffee and then plug in MC delta T, you get, well, this equation, which is the same thing. And then if you expand it out, you get TF. Basically, if you try to use this equation to solve for the final temperature, you're going to have to do all these steps. So I'll give you this one and I'll give you this one. And you can use either one you want. One other thing I need to point out. We said before that K is equal to MC. So I could rewrite this equation as K1 TI1 plus K2 TI2 using my new trick I learned. Okay, I didn't actually, I already knew about this. I just wasn't bright enough to figure out, oh, I should probably use that and my lines will be a lot better. Hindsight, you know, hindsight. All right, so this is the same thing but with heat capacities. So let's say you didn't know your mass or specific heat, but you simply knew your heat capacities. You can use that to solve for the final temperature. And so keep that in mind. It's kind of handy. Your C's, by the way, are never going to cancel out unless they're the same substance. So let's say you have water and water at the same time, then your C's will cancel out. Otherwise, they never will. So keep that in mind. So let's do an example problem. We have a miniature 100-gram iron manatee. It's just something to do. At 300 degrees Celsius, it's placed in 500 grams of water at 50 degrees Celsius. What is the final temperature? So since I'm looking for final temperature, I want to use the TF equation that I used earlier. And just to recall, that's M1 C1 TI1 plus M2 C2 TI2. Using my new trick, over, I'm loving this, M1C1 plus M2C2. Excuse me. Okay, so let's plug in some numbers and let's have some fun. Okay, I'm going to have fun. Hopefully you two do too. Alright, so 100 grams, C1, that's iron. Iron from the table I give you is 0.46 joules per gram degrees Celsius. And then its temperature was 300. And I'm going to have to put this a little lower because I just realized I'm going to run into the manatee. Plus the mass of the water, which is 500 grams. Its specific heat, which is 4.18 joules per gram degrees Celsius. And the final temperature. What is the final temperature? Or, sorry, initial temperature. I said that wrong. 50 degrees Celsius. And then I'm going to use my tool again, but that doesn't really work as well, especially since I'm at a weird angle now. But, hey. Alright, and then we have 100 grams times 0.46 joules per gram degrees Celsius plus 500 grams times 4.18 joules per gram degrees Celsius. Okay, notice a few things. Grams goes away. Yay. So that helps out well. Your degrees Celsius goes away. So grams and degrees Celsius. Oh, that leaves joules. That's okay, because every single argument has a joule in it. So joules is going to go away too. Ah, yes. And then grams again. Oh, yeah, that's good stuff. All right, now what we got left? Degrees Celsius, which will flip up to the top in our case, especially when we move that over to this side. And so we actually have a unit of degrees Celsius, which is what we wanted. Now, I get out my calculator, and I put it into my calculator. So 100 times 0.46 times 300. And then we'll add my 500 times 4.18 times 50. And then I divide that by 100 times 0.46 plus 500 times 4.18, close my parentheses, and I get 55.4 degrees Celsius. Couple things to know. Okay, so it's very close to the water's temperature. The water's initial temperature was 50 degrees. This is only 55.4, but it makes sense. You only had 100 grams of iron, whereas you had 5 times more water than you did iron by mass. Then note that while the iron manatee was really, really, really hot, its specific heat is 0.46, which is a conductor, whereas water is an insulator. So a lot of times when you put something hot in the water, you know, it doesn't really heat up the water too much. Like you have a really hot pan and you have water in the sink and you put your pan in there and it steams up. It doesn't really heat up the water all that much. It's because water is a good insulator. And so it should be closer to the value of water. Alright, let's do another one. We have an unknown object with a mass of 50 grams. An initial temperature of 100 degrees Celsius is placed into 400 grams of ethanol. And I give you the specific heat there. The initial temperature of the ethanol is 20 degrees Celsius and the final temperature of the mixture is 30. What is the specific heat of the unknown object? So I usually like to write the conservation of energy instead as M1 C1. I usually just say delta T1 is equal to negative M2 C2 delta T2. I could plug in the TF minus TI, but sometimes it's more helpful to not do that in my case. So, alright, well, what am I looking for? Okay, so we have unknown object, 50 grams. So I'll go ahead and plug in its mass here. And then we don't know what it is, so we're actually going to solve for C1. It says the initial temperature is 100. And then it says that the final temperature of the mixture is 30. So it's going to go from 100 to 30. So that's going to be a negative 70 degrees Celsius drop. And then that's equal to a negative of the M2. M2 is ethanol. And we had, what, 400 grams of ethanol. Its specific heat is 2.4 joules per gram degrees Celsius. And then its change of temperature is 20 to 30. It's going to be a positive 10. Now, one other thing I kind of forgot to point out. Why did I jump to this equation and not say this equation? because it says I'm looking for the specific heat. It is hard to use this equation to get the specific heat. It is much easier to use this equation to get the specific heat. So let's do that. All right. So basically, I just divide everything out. Notice you have negatives on both sides, so your negatives are going to become positive heats, and you end up getting a positive specific heat. You should get a positive specific heat. Notice that your grams cancels here. Your degrees Celsius is going to cancel over here. And so that gives you joules per gram degrees Celsius when you divide it out, which is the appropriate unit for a specific heat. So I'm going to take my 400 times by 2.4 times the 10, and then I'm going to divide that by 50 times 70, and I'm going to get 2.74. And as far as I know, that doesn't correspond to anything particular off the top of my head, but that is a specific heat of the substance, 2.74 joules per gram degree Celsius. So that gives me my answer. Let's do one more. And I just really like the picture. Don't take the schist for granted. Yeah, I know it's lame, but I really like that for some reason. 100 grams of granite. Okay, I didn't do schist. I probably should have done schist now that I think about it. Yeah, that would have been logical. I wasn't thinking. Hindsight. Okay, 100 grams of granite, where its specific heat's around 0.79 joules per gram degree Celsius, and 100 grams of basalt, which is around 0.84 joules per gram degree Celsius, are each at 50 degrees Celsius and are dropped into a pot of containing 300 grams of water at 10 degrees Celsius. What is the final temperature of the three substances once equilibrium is reached? Okay, so this is kind of a stretch on what we were doing earlier. So I'm going to reverse here and talk about how the fact that we said that delta E1 plus delta E2 was equal to 0. Well, that's just for two substances. If I wanted to add a third substance, I could say delta E3. And if I wanted to add a fourth, I could keep adding them. The conservation of energy is saying that the energies exchanged between all these substances should always equal 0. By contrast, or, well, not really by contrast, but an addendum, there's a better word, I suppose, I could use my TF equation. Before I had M1C1 Ti1 plus M2C2 Ti2. If I have 3, I can say, okay, M3C3 Ti3. And I could keep going and going and going. Using my little cool tool I came up with, or rather figured out, I can do that. And then on the bottom, I will have M1C1 plus M2C2 plus M3C3 ... I only need 3 substances because I don't want to do 5. I mean, as you can see, it's going to get quite tedious. I'm just trying to illustrate a point that we can do more than just 2 objects with this. So let's plug in and go to town on this bad boy. Alright, so we got 100 grams of granite. Hopefully I don't run out of room. You know what? I might. So this is what we're going to do. I'm going to erase what I just did. Scroll down just... okay, I can't scroll down. Well, poopy. Alright, down here. We got this. I got this. So TF is equal to... we have 100 grams of granite. And then its specific heat is 0.79 joules per gram degrees Celsius. Its initial temperature is at 50, plus my basalt, which is also 100 grams. Its specific heat is 0.79 joules per gram degrees Celsius, and its initial temperature is 50, plus water. We have 300 grams of water. Its specific heat is 4.18 joules per gram degrees Celsius, and its initial temperature is 10. And so I could keep going, but I only did 3 because, well, you get the picture. Alright, so then I divide that all by its specific heats, the heat capacities. So that's 100 grams times 0.79 joules per gram degrees Celsius, plus 100 grams times Basalt was supposed to be 0.84. Sorry, I changed that real fast. You were probably thinking, why was he doing what he was doing? Well, I made a mistake. Sorry, I correct it. 0.84 joules per gram degrees Celsius. Normally, I would probably go back and record the video, but I don't really know a way of editing it, and I'm kind of running out of time, so there. Hopefully you caught that. Plus 300 grams, and its specific heat, which is 4.18 joules per gram degrees Celsius. Okay. Plugging this into a calculator. So 100 times 0.79 times 50 plus 100 times 0.84, try that again, 0.4 times 50 plus 300 times 4.18 times 10, and then I divide that by 3 sets of numbers. Looks like we're going to have 100 times 0.79 is 79 plus 84 plus 300 times 4.18, close, 14.6 degrees Celsius. I'm going to go up right here. Okay, once again, very close to the water. Well, a couple things. We had more water than we did both the granite and the basalt put together. So there is that. But once again, water's just got such a higher specific heat that it's just going to end up regulating everything and keeping the temperature close to itself. And so yeah, it ends up being 14.6 once it hits equilibrium. Okay, that is it.